All right. Good morning, everyone. So a little bit of bookkeeping up front. Um, my son had a little minor sprain, and I need to take him to the doctor's office. Unfortunately, my partner is not able to accomplish that today. So luckily, my colleague Tom Steinman will be leading the session at 1 o'clock, talking about opportunities in quantum computing. Right now is the time. There's so much out there, and the opportunities aren't just for PhD students or postdocs. There's undergraduate opportunities in there. There's a lot out there, and so I really encourage you that if you're interested in quantum computing, to begin taking a look at those. For the session at 2 o'clock, I've just linked to an IBM Quantum video with Victoria Lipinska. It's pretty decent as far as a walkthrough with VQE and how to avoid some of the pitfalls with barren plateaus, talking about, whether you're using a generalized circuit versus a bespoke circuit and some things like that, as well as the different optimization methods. Today, we're going to be talking about how to apply error mitigation in circuits. And it's not nearly as complicated as it can sound. This is not a session in how dynamical decoupling or gate twirling is done. It's more a session on just to apply these and kind of giving an idea of the time frames and stuff that this can take. So, we're going to install Qiskit with visualization enabled in the Qiskit IBM runtime. That way we can interface with the actual quantum hardware. All right, we have matplotlib, and that way we can get pretty pictures, NumPy. This efficient SU2 circuit here, that is a encoding circuit that we've covered briefly before. There's various other circuits like this. Sparse polyop, we're using an estimator, that is, we're getting a scalar output. Okay, and the Qiskit runtime service that we connect to the computer. And something we haven't talked too much about is session versus job versus batch. All batch is being able to bundle a set of Qiskit jobs into one thing to run them at the same time for efficiency purposes. So let's talk about what we're doing here. I'm specifying that I have 10 qubits and that I'm only doing one repetition. Then I encode my circuit with this efficient SU2 circuit. I have pairwise entanglement. And my reps is equal to 1. So I'm just going to draw my circuit here. Okay, we have these parameters in here. This is a circuit that this is building for us, where it's encoding the features for us. Now, I'm going to make an observable here. Okay, where I'm making a sparse polyop from a list. Okay, and so this is just Z on everything with a weight of 1. Now, a mirror circuit is a technique where you take a circuit and you do the inverse of that circuit. Every one of these gates is invertible. If you apply an X gate then another X gate, you end up where you started. And so what you can do is you can flip your circuit and mirror it to get you back where you wanted to start from. Now, there's a couple of reasons that you might want to do this. One is that this is a way to kind of test the noise of a system. Hey, if we do a bunch of operations that should return it to the ground state, we can really simply measure how far off we are. Sometimes you want to uncompute things that you've done and reuse parts of your circuit, so you can mirror that part of the circuit to return it to a ground state and continue from there. So, I'm using a random number generator here to initialize my parameters between -pi and pi, because that's the rotations that you can do. Okay. And then I'm assigning those parameters to my circuit. So all these thetas now are these values between -pi and pi. All right, I'm having a barrier here, and this is, for our purposes here, just visually, that way we can see where the circuit mirrors, where it gets flipped back around. You can use this in circuits if you need one portion to finish computing before you start another portion, but we haven't covered that too much, and I wouldn't worry about that. Okay, so we construct this mirrored circuit using unitary overlap, where this is just a function that applies that mirror, and then we're just going to draw it. And all it is it's our circuit forward and then our circuit backwards. Okay, so now we're going to optimize this problem for hardware execution. This is just me signing in to the IBM account. You'll use your API key and your CRN, which you can get off your IBM Quantum account. I sign in. I set up my Qiskit runtime service, and I'm using the least busy backend, all right, which is IBM Fez. Okay, I make my pass manager and I set my optimization level to 3. That is that it's going to optimize this circuit as much as possible. Another fact here is that with optimization level 3, this enables you to use a lot of built-in error mitigation techniques. So instead of you trying to manually create it or anything, you can just call, zero noise extrapolation or dynamical decoupling. All these methods of error mitigation that we have. Okay, and so this is what it looks like whenever it's converted into that instruction set architecture, the architecture that's actually on that quantum computer. So it looks like we have some square root of x operations here instead of our R and phase operations. Okay. So now this is in language that the quantum computer can understand. All right. We are applying the layout of our circuit to our observable. That way it matches. Okay, and we're going to run the circuit. So I create this primitive unified block. This is the instruction you pass to run a job. Okay, for this estimator, it's just the circuit and the observable because I've already assigned those parameters. I'm not updating those continually. We could add a set of parameters if we needed those. And so I start a IBM batch. All right, my estimator is equal to that estimator V2. I'm doing 100,000 shots, and I'm saying the resilience level 0. That means no error mitigation. All right, I'm going to run that primitive unified block, that set of instructions on how to run the circuit, and that's my job. Okay, now I'm going to make another circuit where I'm going to enable dynamical decoupling. There's various different types of dynamical decoupling sequence types. I believe XPXM is the default and is just what will be there if you just say true. All right, and I'm going to run this job, and I'm going to pin job 1. Then I'm applying measurement mitigation. I run it, and then gate twirling. It's just twirling.enable gates equals true. Number of randomizations is equal to automatic, and I run that job. And then I'm running zero noise extrapolation. So we have with no error mitigation, then we have with dynamical decoupling plus dynamical decoupling plus our readout error mitigation, dynamical decoupling plus readout error mitigation plus gate twirling, and then all of that plus zero noise extrapolation. So this is just me post-processing these results. I'm pulling out my expectation values, the standard error, this STDs, and I'm plotting it. So this plot's not very informative, but we can see here how significantly this changes. Now this is a pretty basic circuit that we made. It's 20 gates or so deep, but at the same time, if anybody's done any work with, machine learning and stuff, adding 2% or 3% noise can vastly change how well your machine learning works. And so we see that, no mitigation, we had, 97.5. With dynamical decoupling, we got closer to 98. With readout error mitigation, we got above 98. Then just by adding twirling, we reduced, and these are things where you need to run these experiments to see how the error mitigation affects it. And then when we added zero noise extrapolation back in, we achieved nearly 99%. But we do also see that this standard deviation is increasing a little bit. Okay, now that was only on 10 qubits, which is a relatively small circuit. And so this morning I ran it on 50 qubits. Okay, all of this is the exact same thing. I set up a circuit with 50 qubits. I use my efficient SU2. Okay, I apply that mirror circuit with using the unitary overlap. I transpile the circuit to the hardware to use the gates and to work on that hardware. I create my primitive unified block of the circuit and the observable, okay? And then I run it, 100,000 shots, all right? And so I do, no error mitigation, dynamical decoupling plus readout error mitigation, and then plus gate twirling, and then plus Z&E, okay? And so once again, it's all pretty close to 1. Let me scale in a little bit here. And here we're seeing huge amounts of difference. Whereas previously twirling was our least productive thing, whenever we just added dynamical decoupling, we reduced an error because we're adding gate operations with that dynamical decoupling. So it's one of those things where we have to evaluate sometimes that is that crosstalk where one qubit affects another one, causing more errors or less. And so it seems that in our circuit on this hardware, and remember, each hardware is different on the amount of crosstalk and stuff. And in previous sessions, I've talked about how to characterize that by taking a look at those back-end properties. But then we add readout error mitigation, we add twirling, we add zero noise extrapolation, and even on 50 qubits, we still get pretty close to 99%. The standard deviation still increasing, but even at the low end of the error threshold with zero noise extrapolation, we're superior to any one of the previous iterations. Another thing that you might want to do is you may want to see how much each one of these is contributing to the mitigation of errors. So here I was just adding them all together, but you may want to take a look at how much is each one of these separately contributing and affecting. These things take time and things like that. All right. Now, with this, I was using up a lot of my quantum time. If you just run this notebook up to this point with 100,000 shots, it'd take about, 5 to 7 minutes. It's the end of the month, and I might as well use up my 10 minutes of quantum time. So I was fine with it, but as I wanted to demonstrate how each one individually contributed, so I lowered the shots to 10,000. So it's a less rigorous measurement, but at the same time, we can still get a good idea. So this time, instead of just adding it, for each step, I turned off the previous one. So we have no error mitigation, just dynamical decoupling, just readout error mitigation, just gate twirling, and just Z&E. Okay, and so here's what we saw. So once again, the dynamical decoupling, it doesn't seem like crosstalk is contributing as much error as we saved by using dynamical decoupling. And then if we take a look, just the gate twirling seems to be having the greatest effect. And so if you're trying to budget your quantum computing time, or whatever the case may be, it looks like Pauli twirling on these gates, which is a measure to prevent those coherent errors. I've talked about that, like, hey, we have those resonance cavities that Dr. Mukesh talked about. That's how we are doing these gate operations. We're sending in these microwave pulses. So sometimes they don't do the exact amount of rotation you want. There's a small error in how much it rotates that, and twirling seeks to negate that. And it kind of makes sense given the large amount of single gate operations we have in our circuit. Okay, we do have some entanglement here, but we have tons of these single gate operations in our circuit. And so these single qubit gates are what's contributing most to our error. So it makes sense that Pauli twirling is contributing most to reducing that error. And additionally, this standard deviation bar, being relatively small compared to the rest, is good news on ways to reduce the total noise of our system. So relatively short session today. And I know we're all learning and getting comfortable with Qiskit, but that using these error mitigation techniques doesn't take hundreds of lines of code or anything like that. As long as you where is it at? Here we go. Nope. Keep going. Our pass manager. As long as you use optimization level 3 with your estimator, Okay, it's relatively simple to turn on dynamical decoupling. Dynamical decoupling.enable equals true. All right, it's relatively easy to turn on measurement mitigation. And so as you get comfort with being a quantum computing engineer or whatever the job title is that you like to apply to it, you can see that, hey, as you're simulating your experiments and things like that, it's relatively easy to test out these different measures of error mitigation and to try to determine which one of these has the biggest impact on your system. Do I have any questions from anybody? All right. Well, I'm giving anyone a chance to write a question if they'd like. Warning is that the notebook, if you just run it, you're going to use 5 to 7 minutes of your quantum computing time with all that folding and all those shots and all those comparisons. That, hey, if you're running a 50 qubit circuit, 100,000 shots and doing it you know 5 times, you're going to eat up a fair amount of your quantum computing time. So keep that in mind as you're moving forward. However, error mitigation is essential with quantum computing. It's errors a part of the system, and we have to be intelligent in how we apply it. So you can characterize the noise of your system using those back-end properties, like I demonstrated in a previous session, to understand what kind of noise has the greatest effect. You can specify certain qubits that you're using, and then you can apply these error mitigation techniques. Noise. That 2 qubit error is the biggest factor. That 2 qubit error. The zero noise extrapolation is very helpful with that, as well as the Pauli twirling. But 2 qubit error is what accumulates noise in your system generally the fastest. It's one of those things whenever I'm creating a circuit, of course I want to know how wide it is, how many qubits it is, and what its actual depth is, the layers of gates that it has. But another metric that I'm always looking at is 2 qubit depth. How many layers of 2 qubit gates are there? Because that's what's going to drive error the most in our system. And so that's why, in that example I gave where we had the star connection of 2 qubit layouts versus that linear one where that way we weren't having to do swaps. That's why we have to do those things. Hey, if we had an ideal quantum computer that had unlimited connectivity, that every qubit was connected directly to every other qubit and it worked great, yeah, we would, be able to, with reckless abandon, entangle our system to exactly represent the type of system that we wanted. But that 2 qubit error is that sticking point where we have to be judicious in how many 2 qubit gates that we apply. And so it's and that's also why we have all these different methods. Different quantum circuits have different exposure to different kinds of noise, and even from hardware to hardware. It may be that today I'm running on IBM Fez, and I decide that I can get away with just zero noise extrapolation or readout error mitigation. But tomorrow I'm running on IBM Marrakesh or something, and because the qubit's available to me, I may need to change my noise strategy. Oh yeah, yeah, yeah. So it's one of those things where, sorry, I need to read these questions out loud. Do you think that this will decrease as this technology improved, or will we just see it on a larger scale? Both. We're getting better and better about maintaining coherence in these systems. That's the big change, and it's the Eagle processors are being kind of timed out, and now that we're mostly working on Heron processors. And I mean, the difference is just absolutely huge on the reduction in noise that we're seeing. So we're getting more qubits while we're getting more coherence on those qubits. Whenever the Nighthawk class processors come out, they're going to have a higher connectivity of the qubits. So every qubit will be 4 connected, which is going to be huge because that reduces the number of 2 qubit errors. And then, of course, on the horizon, 5 to 10 years away, hopefully, we have fault-tolerant quantum computing, where we have enough qubits available to us that we can have a logical qubit that represents, maybe 10 or 12 physical qubits, and that we're correcting these errors as they occur. Now, here's the thing. I think it's going to be a long time before you don't have to think about noise, but noise is definitely getting better. All right. Oh, awesome. Yeah, you're welcome. So at 1 o'clock, Tom Steinman's going to be talking to you guys about some of the opportunities in quantum. And I mean, this is just a slice of what's out there. There's summer schools, internships, careers that are open. And it's not just to PhD students and postdocs, people with bachelor's degrees, people with even less than bachelor's degrees in some positions. There is opportunity out there. This field is growing. So, I mean, please take a look at that and kind of get an idea of what's available. And I just posted an IBM video because my son had a minor sports injury and I got to take him to the doctor. I appreciate y'all's patience with that. But I'll be keeping an eye on Discord today, and if nothing else, I'll see you all tomorrow. Thank you very much.